Okay. Other questions? We saw that this is the Flyback converter, just a direct straightforward derivation from the buck boost converter. And probably you also can see now why it's the most used converter. Because we don't add one extra magnetic element, one transformer to our buck boost converter. We just change a little bit the magnetic of our buck boost converter. Instead, in a buck boost, you have single winding over a magnetic core. In a Flyback, you have two windings on the same magnetic core. So it does not cost too much more than a buck boost converter. The only change is that instead of having a core, magnetic core with one winding, you have a magnetic core with two windings. But diode is still there, output capacitor is still there, input capacitor is still there, and you have advantages. The advantages are transistor, switch is moved to the low side. Advantage is that you have NP over NS that you can play with in order to move stresses, in order to have a good duty cycle, and so on. So this is the most used, the most common topology you find, because it's basically inexpensive. Only one magnetic. Unfortunately, it has to be run in DCM, so you cannot go too much high power. But for many small applications, that is the most convenient way. And you have isolation, because this transformer, these couple inductors, give you isolation. You don't want to lose isolation because you pick your feedback from here and you go back to the primary side. But this is a different story. Oh, transformer is not the only way to have an isolation from the mains. There are also different techniques to have an isolation from the mains, but not in this class, sorry. Okay? What if instead of a single output voltage you want many output voltages? In order to add one extra voltage, output voltage, the change to be done is very easy. It's very simple and inexpensive. Because you still have your primary converter dot up, first output winding, E not 1, and dot down. If you want a second output, you put a secondary, another secondary winding over here. C01, C2, dot down, and here you have NP turns, and S1 and S2. And here you have the up2. And what do you want the third output voltage? And you put the third winding, one diode, one capacitor. For each output, extra output you want, you add one winding, one diode, and one capacitor. The cost to increase the number of outputs is really minimal. And S1 and S2. And this is still an indirect converter. It's still a buck boost, some of a buck boost. Because when you close the switch during T1, the switch is closed and current flows like this, and you are charging energy inside, loading energy, storing energy inside the inductance, primarily the magnetizing inductance. And during this phase, during T1 phase, you have the negative over here, the positive over here, the negative over here, the positive over here. So all the output diodes are open, and the loads are just leaving during the energy stored in the capacitor. During T2, when you open the switch, well, the switch is open, and what happens? If you want to say it in terms of magnetizing inductance, you can put your magnetizing inductance over here. This is LP. It's just a symbol. LP is inside, is merged inside the couple inductors, but we can just detach them to show what happens with LP, and here this is just an ideal transformer with no input inductance, no magnetizing inductance. What happens is that during V1 you had current flowing down to LP because you applied a voltage over here and you had this current coming down. When you open the switch, current was flowing to inductance and keeps flowing to the same inductance. And during T2, what happens is this current keeps flowing the same direction through the magnetizing inductance. I do repeat, this is just a model. This is what you get if you have an ideal transformer with the infinite magnetizing inductance and you put an inductor outside on the primary side of this. You don't do this, everything merges together. You build this magnetic component using a low permeability core, or you put a gap, because those are merged together. But from a principal point of view, from an ideal point of view, you have this current going down during T1 because you charge it. During T, when you open the switch, this current was going down and keeps going down. But this time the switch is open. So when it comes over here, the magnetizing current, instead of going to the switch, it goes to the ideal part of the transformer, the inner transformer. And so you have current entering the non-down side of a winding. That means that here you will have a current exiting, coming out from the non-dot part of the winding. So we have current coming out from here, and this current coming out from here, and charging the out. Power in the out. You still have an indirect converter. First you charge, then you deliver. Okay? So far so good. And all the secondary windings are activated, are powered at the same time by this energy that looks for an escape path. Let's start to design these transformers. If we have multiple outputs, we need to find out NS1 over NS2, the turn ratio between the different windings, secondary windings. We need to find NS1 over NP, the ratio between primary and secondary windings, and we have to find LP. Those are the three numbers we have to specify for this component, magnetic component. Everything else is already has been already analyzed in the past, because we know that the switch current is just our triangular waveform that starts from 0, climbs up to a peak value and stops. We know the current to this diode is just coming down triangle. We know how to find the ripple, how to find the output ripple, how to find the RMS current flowing through here, the RMS current of a triangular waveform minus its DC, and so on. We need these three numbers now. First number, first parameter, specification we have to tell our magnetic designer is the turn ratio between the different outputs, the values outputs. That is NS1 over NS2. And remember, this is our circle. Dot down, NS1, NS2, V2, V0, 2, V0, 1. Looking for this turn ratio. That's easy. It's easy because each single turn of this winding sees the same flux, the same magnetic flux by M in the transformer, in the core. And each single wire, each single turn of this secondary wind, secondary, sees the very same phi, very same flux to this to the magnetic core. It means that when I open the switch, the flux starts to climb up from 0 to a maximum, and during T1, and during T2 the flux comes down because it's delivering energy. It's losing energy, so it comes down. But the flux variation, this is the d phi by dt, the flux variation, the flux change, is the same for each turn of this winding and for each turn of this winding. All windings, all turns, each turn of each winding experiences the same flux change. What is d phi by dt?
The voltage.
This is the voltage induced across one single turn. This is the voltage per turn. Each turn generates this voltage. So if you want that these two output voltages are the same, you need to have two windings that have the same number of turns. If these two number of turns are the same, if ns1 over ns2 equals 1, it means that the two voltages generated, created, induced on the secondary windings are the same, and the two output voltages will be the same. Okay? And what if I want a different output voltage? Well, I can say if I want V1 equals twice as much V2, I could imagine that this winding must deliver the double voltage, must have the double number of turns with respect to this secondary winding. Well, it's not really like this, because from this point on we start to be real engineers, at least we try, and we have to consider losses, we have to consider secondary effects, etc. In particular, over here, we have the direct voltage drop. VD. VD is something that we lose between the secondary winding voltage and the load. So I can write down that NS1 divided by NS2, the turn ratio between these two windings, must be equal to the ratio of the output voltages, but not the output voltages alone. Output voltage plus VD. So it will be V output 1 divided by VD1, and this is divided by VD2. Why do I put the two different, possibly different direct voltage drops? Because one output could be a low voltage output, let's say 5 volts, and so probably with the 5 volts output voltage I can use Schottky diode over here. And the Schottky diode has a voltage drop that is around half a volt. The other output could be a 24 volts output, a 48 volts output for some like a relay or something like this. And so this output voltage could require normal NP diode, not a Schottky diode, and so this voltage would be 1 volt. In any case, you have to make this ratio, and this ratio equals the turn ratio between the different secondary windings. There is one extra thing to take care of, and it is that NS1 and NS2 are integer numbers. You cannot wind 3.72 turns. It's either 3 or 4. And for low voltage outputs, in some cases, it's difficult to find two integer numbers that give you this ratio. So in this case, you have to increase the number of turns above the minimum that you have to guarantee in order to find a ratio, a ratio of two integer numbers that are very similar. Don't worry about that, because that won't be in your final exam. Final exam, I just need NS1 divided by NS2. Everything else is a problem of the guy who designed the transformer or the magnetic or the coupled inductor. So You have to know that it exists. If you find that one output is 2 turns, and the other one output has to be 2.7 turns, you can get it. You get 2 and 3, or you get 2 and 2. If this with 2 turns gives you, let's say, 1 turn gives you 5 volts, and you want here 12 volts, no way to get it, because if you put 2 turns, you get 10 volts. If you put 3 turns, you get 15 volts. Minus this voltage drops. But this is the basic idea. You are not going to be very fine in your ratio unless you increase the number of turns in the secondary windings. If instead of having 1 and 10, you get, for example, 5 and something else. 5, you can have here 12 turns, and you get something closer to 5 volts, to 12 volts. But it's not your problem by now. You have to know that it exists, but it's not your problem. So, turn ratio here is 60. What else do we need? What's the problem? What else do we need? NS1 over LP, the turn ratio between primary and secondary windings, and LP. Let's start with LP. But we can start as well as NS and NP, the same problem. How did we design LP in a buck-boost converter? Well, there was an equation like LP L equals, it was not LP at this time, it was just L, equals 1 minus T squared times R divided by 2 switching frequency or something like this. That was an ideal relationship, and that was for CCM, and then we said if we take an inductance that is larger than this, we get CCM. If we take an inductance that is smaller than this, a critical inductance, we get the DCM. And in that case, how much was the duty cycle? The duty cycle was depending on the ratio of the output voltage divided by the input voltage. But here we have the turn ratio. Turn ratio helps us. It means that we can choose our duty cycle, or we can choose to move the stresses around, and we still have a flyback converter, exploiting the turn ratio degree of freedom. In this case, in order to determine LP, what I usually do, then remember, this is a design. So every time you take a decision, you go on with this decision, making your calculations, and you can end up with something that is not feasible or is not convenient. So you have to step back, say, okay, that choice, let's change my initial choice and go to a different way with different parameters. And here, what I do is, that is my initial choice. If nothing else works, this is what I can assume at the beginning. To find out LP, what my initial choice is, well, the system must be DCM. DCM means that D1, what is D1? D on, D, duty cycle, plus D2, what is D2? T2 divided T off. T2 divided by T switch. Here I go with duty cycle, but if you want to go with times, it's okay. Must be less than 1. Strictly less than 1. Because I don't want to go with CCM. I don't want that D1 plus D2 is far, far smaller than 1. I don't want that D1 plus D2 equals, let's say, 0.5. Because if D1 plus D2 equals 0.5, it means that I pay for the magnetic, and I use the magnetic only at 50% of its time. I waste the performance of my magnetic. So I need, for the same power that I transfer, a larger magnetic because I don't exploit it 100% of its time. I cannot go to 100%, but something like 80–90% would be reasonable. So my initial choice could be, if nothing else prevents me from this, but I will discover only at the end, is that D1 should be around, D2, let's see. Do I want to charge fast my magnetic energy in the magnetic field and discharge it slowly, or do I want to charge it slowly and discharge it fast? I don't know, but Romans said something like in medio stat virtus. That means the sports society Virtus is in downtown. No, la società sportiva Virtus è in centro, in medio stat virtus. No, it means that if you take an average, something in the middle, probably you're not too far from a reasonable result. So it means that my two duty cycles, the charge duty cycle, the charge fraction of time, and the discharge fraction of time are more or less the same. I could assume here something like, let's say T2, let's say 40% or so, and T1 40% or so. Both maximum T1 and maximum T2 around 40%. If you don't like this 40%, you want to go to 45, be my guest. If you want here to go to 45, don't be my guest, don't like it too much. But something like around 40. We use our magnetic for 80%, 85% of its time. That's a good expectation. Not only, but I can pick a value for the switching frequency at the beginning. Because not only the cycle is important, but also switching frequency is important. And here, once more, we have this normal limitations we have for buck-boost converter. The higher the power, the lower the frequency. But here we have some extra troubles with the leakage inductances. My coupled inductors are not perfectly matched, perfectly coupled. They are not with the coupled coefficient of unity. They are slightly uncoupled. There is some energy that is stored in the core that is not retrieved by the secondary arm. This is the coupling factor mean. This means that I have some leakage inductances, and this leakage inductances prevent me from going too high in frequency. And my frequency could be in the range up to, I don't know. I don't want to give you a number as usual, but it could be in the range of, let's say, from 300 kilohertz down. It depends on how well you can with your magnetic. That is not free. So I start with my switching frequency and duty cycle, and then I have to go to check what are the requirements of my on my circuit. Do you remember what is LP used for? What is the inductance in a flyback, in a buck-boost, used for?
Store energy.
Store energy. I want to be able to store for each cycle enough energy to provide all the power at the output. So, we have first to look for the total output power. Once that we have the total output power, we go for the total input power. Is the input power the same as the output power? In an ideal world, yes. In a real world, no. Because in a real world we have losses, we have efficiencies. So we have to consider this. I don't know very well, very precisely how much will be my loss, how much will be my efficiency. But I can give an estimate, at least a guess. Once that I have my input power, I can find out the energy per cycle that I have to store inside my converter. And from the energy per cycle, I can eventually get my inductance, magnetizing inductance, private inductance LP. Because remember, LP must have a very precise value or a maximum value, a little bit less than this is okay, in order to be able to store enough energy. So let's look for output power. The out is equal to that output.
Mu square over R.
P
The sum of
is the sum of all the single output power. That is summation on all output of what? The output voltage times the output current. Which output current do we take? Minimum, so and so, maximum.
medio satellittus. Medio satellittus.
Medio does not start with maximum. Obviously, we have to guarantee that we can deliver the maximum output. So, I of max. This is basically just simple. In some cases, you could say that, oh, if my first output is delivering the maximum current, the second output for what my load is cannot absorb any power or cannot absorb the maximum power. You can have some kind of what we call it. It's the it's not something of power electronics. It's something of electric systems. You can have the power absorption and power consumption of each absorption from each output is not at the same time. It's not contemporary. It's not at the same time. It's called I forgot. It's something related to the power distribution, not to the power electrons. Anyway, you have to find out the maximum output power. The maximum secondary power, the power that the secondary has to provide, is not just this one, because we have losses in between. And the losses between the secondary winding and the load is given by, or are given by, what is between secondary winding and load? Diode. So the secondary power should be summation on all output of V naught plus VD, V naught I, VDI, times IOI max. We have to consider the diode voltage drop. Could be half a volt, could be 1 volt, but it's there. And how much is the primary power? The sub P means primary, sub S means secondary. How much power do we need to store inside the primary in order to be able to, how much power should be stored in the primary in order to be able to provide, to supply all this secondary output? Same. PS, secondary power, if everything is ideal. If you find a manufacturer that can give you ideal transformers and ideal copper inductors, let me know, because I am in desperate request for that. But, there's an efficiency, magnetic efficiency of your magnetic components. Your magnetic components is made of copper wires, and when you have current flowing through wires, you have heat, you have power dissipation. When you have a magnetic flux, magnetic induction going up and down in a magnetic material, you have power dissipation. So your magnetic component has an efficiency, very high usually, the order of 92, 95 or more percent, but it's not in unity. Not only, but you have some extra power losses that are due to the magnetic component, but are not lost inside the magnetic component, are lost in the switch. And this is related to the magnetizing inductance. So here you have to divide by the efficiency of your magnetic component, and this efficiency could be, it's not really all power that is lost in your magnetic component. There is some extra effect, but could be in the order of magnitude. If you do something reasonable, it would be 0.9. If you build a very good copper inductor, it would be 0.95, but I usually stay on this number, more or less. If you manufacture a very lousy coupled inductor, just change, look for another job. That's not a good idea. Something like 0.9 could be reasonable. This is the power that you have to inject into the primary that will be delivered to the secondary. Well, not all of it, because part will be lost inside the winding, the copper resistance. Some will be lost inside the magnetic, the ferrite, or the material, the magnetic material, the core. Some power will be lost by the switch due to the leakage inductance. But you can put this number, consider all these effects. More or less, that is just a first design. So now we know how much is PP, primary power. What should we do? Each cycle of work in our system. We do not inject a power into the primary winding. We inject the energy. And the energy multiplied by the number of times we make this operation per second gives me the power. So the energy that we have to inject on the primary winding, to store on the primary winding, is equal to what?
PP over
The primary power divided by the switching frequency. This is a requirement. I know how much is the power that they wanted to deliver on the loads. I know how much power must the secondary windings deliver, how much power I have to inject into the primary winding, and now with the switching frequency, know how much energy I have to store in the primary winding. And the energy in the primary winding equals 1/2
square.
LP times IP squared. P. And I want to find out LP. This is the primary current versus time. Initial value of the primary current is 0. And this ramps up with a slope that is V in over LP, that I still don't know yet. That's really true. V A over LP means that you assume that all this voltage goes completely across the inductance. Is it true? No. There are 3 reasons why not the A goes across the LP. And the 3 reasons are maybe 2 only. Switch. We have a voltage loss across the switch. The switch, yes, sure. How much is the switch? You decide it. Should not be too large with respect to the VE, but should not be 0. Not be 0 because it's impossible, but cannot be, let's say, 1.1% of the input voltage, because it means that you use a large, huge switch, and so it becomes expensive, difficult to drive, etc. What is across the switch? Yes. One more reason why you could have an input voltage and primary voltage that is not equal to input voltage. Voltage drop across the sensing resistor. If we are in current mode and we have here our RS or a transformer that goes to RS, we have a voltage drop over here as well. And so my equation It's not just V in, it's V in minus V switch minus V at S. And this is, those are simple terms to put in our equation. There is one extra. And the extra voltage drop that reduces the input voltage is the voltage drop across the winding resistance. This is the winding resistance, because the winding is copper, and copper has a resistance. So we have some extra voltage drop, resistive voltage drop of the primary, and this resistive voltage drop is something that is subtracted to the voltage that goes to on the inductive part. We don't consider this because we don't know how much it is. Using all these coefficients like 0.9, etc., probably we'll just include this part, but we have to check it. So, my equation, my slope, let's go back over here, it's not V over LP. V over LP was the ideal situation, not ideal anymore. That is V minus V switch minus, if we are in current mode, V of X over LP. And this is divided by, this lasts for a time that is T1. Or V1 over the switching frequency. What are my limitations on this graph? What I have to consider when I draw this graph and I start to make the calculations over here? Well, first limitation is V1 is limited. Not by the ratio of the output voltage and the input voltage as in a buck boost converter. This V1 is free, I can choose it. But I have to take a reasonable choice and I cannot go above or far below this choice. And my choice, initial choice, is that V1 max equals, what did we say? 0.4, something like this. 0.4 is a reasonable, 0.45 if you like twist. 0.4. And so we know how much is T1 max. Because T1 max equals 0.4, 0.45, whatever it is, divided by the switching frequency. We already selected the switching frequency. When do I need the maximum duty cycle? When do I need to extend as much as possible my duty cycle?
When the resistance of load, when the resistance of load decreases. So
when the load is taking the maximum power, sure, but we already included it because if you check what we did up to this point, we started from I max. So here in this condition there is already the maximum output power. And this maximum output power just came out, just referred to all the conditions to this PP and to this equation. Here inside, the numbers that I will get here inside derive from this value of energy, that derive from this primary power, that derive from the maximum output power. So this is one condition. When the power goes up, the output power goes up, my duty cycle increases for sure. Second condition. Second fact that could change my duty cycle.
change of weight.
Input voltage. Input voltage determines this slope. And what I want to get is a given big value in order to get enough energy. So if the input voltage goes down, I need to extend T1 in order to accumulate enough energy, in order to reach the maximum current that I need to accumulate this energy. So the condition for my that goes with the maximum duty cycle is the minimum input voltage. cannot do whatever I want. I am limited in the time that I have to store energy with heat. This is my limitation. And with this limitation, I can derive E, knowing the energy and knowing the max T charging time. We already did it, I think. But let's do it again. Energy stored in the primary inductance equals 1/2. And this is what we are lucky. We know how much is 1/2. 1/2 is 1/2. Times LP. I don't know how much is LP. Times what? IP squared. I don't know how much is IP. So I have two unknowns and one equation. But here it's not so bad, this equation, because this is equal to 1/2 LP. I don't know LP times how much is IP. Just look at the graph over there. IP is this one. And I have a finite time, a maximum time to charge it up. And I have a slot that I can go away. So, let's see what happens. IP is equal to V in minimum minus V switch minus VRS if we are in current mode. If we are not in current mode, this is not there, divided by LP. What is this expression?
No, the slope.
This is the slope of the rising current, multiplied by the duration of this slope, we get the peak value. And the duration is D1 maximum divided by the switching frequency. Everything is squared. Now we are okay. Do we know V minimum?
Yes.
Who tells you V minimum? Specs, me. When I give you an exam, a written exam, V is specified. Who tells you V switch?
Switch frequency.
V switch
No, sorry.
is your choice, your designer choice. Is related to V minimum, a few percent of V minimum. Who tells you VRS? It depends if you go into current mode, low current mode, this VRS is there. If you use a standard IC, it's 1 volt. If you use a current transformer, it's 1 volt divided by N. Who tells you LP? No, D1 max is your initial choice. 40%, something like this, then we are ready to step back and change it if we don't like what we get. But this is our initial choice. And this switching frequency is what we selected at the very beginning, square. This energy, we know it. This energy, EP, is equal to the power on the secondary winding divided by the switching frequency divided by eta, magnetic. I just substituted the last two equations on the left. So we have power of the secondary divided by switching frequency divided by eta, that is the energy that I want, equals 1/2 LP, that is what I am looking for, times V in minimum minus V switch minus VRS times D1. Everything over here is squared, divided by LP squared divided by the switching frequency squared. This square and this LP cancel out. This square and this switching frequency cancel out. And I have an equation that gives me LP. That's what I was looking for. And if I solve this equation, that is difficult to understand, but I move LP to the left, I move LP to the right, and I get that LP must be equal to, just help me out, otherwise, Vn minimum minus V switch minus VRS if we are in current mode. Please don't design the system in voltage mode and put this VRS because it's not right. Times V1, everything is squared, divided by LP move to the left. There is a switching frequency, there is a factor of 2, switching frequency PS, and here there is an eta magnetic. Okay, is it right? Let's check if it is dimensionally correct. And to check if it is dimensionally correct, it's easier if we imagine that this switching frequency is on the left hand side. So we have switching frequency times inductance is an impedance. And we have a voltage squared, because D is dimensionless and the eta is dimensionless, voltage squared divided by power. Power divided by voltage squared is an impedance, and it's equal to an impedance, yes, it's okay. So we have LP. And just observe, for example, that every time you introduce one extra loss, this LP goes down. If your efficiency decreases, your LP goes down. If you switch voltage switch, your VRS increases, that means you have less voltage at the primary winding, your LP goes down. Why this? Because we are in the condition of fixed limited time to charge my inductance. If I have a limited time to charge my inductance and I want to store more energy, I need to decrease the inductance, because if I decrease the inductance, the slope increases, the current square increases with the square, and decreases with the linearly, and I have this increases with 1 over P. This decreases like P, but there is a square, so there is 1 over P squared, and the energy depends on the 1 over P. This is not intuitive, but this is what happens because we are limited in time to charge my system. Okay, this is the LP. What else do we need to find out for our magnetic component?
The ratio by NS1 and
we need the turn ratio between input and out. We need NS over NP. NS1. Or NS whatever you want. If you have only one output, you could be tempted to use the turn ratio to see how much current goes to the secondary winding, etc. Just don't follow that path, because for one winding is okay, for two windings it's just impossible to solve.